Okay, so this lecture is once again an application. I guess it's partly a historical lecture, but there's also a lot of interesting material here that one can still use. It also relates to other proof assistants because the original development of hardware verification was done using the Hall system. And I'm quite happy to, in this lecture, telling you about work that was entirely done here. It's really quite transformative work, mostly by Mike Gordon, by him and his group, doing things that were probably thought to be impossible at the time they started out. I'm also going to try and give some more general lessons about how we use formal tools to talk about real-world things of any kind. And remember, a computer, a piece of hardware, is ultimately a physical thing. So we have the idea of modeling a physical thing in logic. Then I will look in particular at how hardware was verified in higher order logic. And then finally, kind of to fill out the hour, so to speak, we will look at a few other little bits and pieces of ESAR. So I just want to remind you, I probably said all of this, so those of you who had logic and proof with me, I would have mentioned the same things because I tend to be repetitive. Modeling is how we do science. So back when people studied physics, they always were playing with frictionless pulleys and planes and things of that sort, which you could say they don't exist, but they make your calculations simple. These days, people talk about, let's say, modeling of COVID-19 and complaining that models were, again, maybe they were wrong, maybe they were too simplistic. Or the very interesting case of climate modeling, which people have been doing now since about 1970. And it is actually possible now to make a scorecard for climate modeling, because if you make a prediction in 1970 about what the climate will be like in 1990, that's all ancient history now. So it is actually possible to validate these models. In fact, a lot of that work seems to have checked out pretty well. The criticism that people always make is that models are too simple. And a kind of a really dumb question is, why do you use models at all? And the answer is, because in mathematics, right, the real world is not itself mathematics. But the very act of transforming the real world into something that we can look at formally using mathematics involves removing it from this physical world into a mathematical world, where necessarily you will simplify a lot of things. And of course, the question is, how simple is too simple, or how simple is still simple enough that you can do stuff without throwing away necessary details so that your results will be meaningful for something. Now, when we're doing this in logic in a theorem prover, we will normally use definitions as always, so we will define things in terms of other things. Very occasionally, you may indeed find yourself using axioms to talk about some aspect of the real world that you can't think of any way to define in terms of something else. And yes, these 2 points at the bottom of the slide are maybe the most important. Clearly, a really slick, elegant model, which is probably a simple model and might make you feel good, but if it doesn't really match the real world very well, then you're going to prove crazy things. And this is already true in this simple world of physics, where you have frictionless things, and so you have all kinds of perpetual motion machines, so you could just make something where a ball rolls down a slide and up the other side, and it will do that forever because there's no friction. So you need to be aware that the things you prove about your model are going to reflect the assumptions you built into it. The other thing, if your model is somehow inconsistent, that is to say, if if the things that you're assuming are actually not possible at all, in other words, there are in fact no instances of your model and you haven't noticed this, then everything will hold trivially, and that's also kind of sad. And just a reminder, we are always dealing with approximations. Now there is a lesson here. So way back in the 80s, when Mike Gordon was doing his hardware verification and using the whole system, he made a lot of assumptions which were the equivalent of frictionless pulleys. And at least one of his colleagues said, that's not so good. Why don't I make a slightly more detailed model in which we have something like more realistic signal strengths and so on that looks a bit more like real circuits. And the problem is, yeah, that's cool, but too detailed, nobody wants it. So in fact, I'm not aware of any work at all in hardware verification that cares about the electronic properties of these digital circuits. So this idea of hardware as having only zeros and ones seems to be the one that people really want to use. And when it comes down to electronic properties, which this will then relate to different kinds of errors like, do they have still things like whether a gate can drive the relevant number of inputs, that kind of thing. I can't remember fan out and fan in, they used to call it, way back in the dark ages when people had things like TTL in the 80s. Probably don't even know what TTL is anymore. Those would be electronic properties, but they can be checked without, you don't need logic to check that the output of a gate doesn't go into more than 10 inputs, right? So you don't need such a sophisticated model just for that. So anyway, yes, Mike Gordon and Paul came from this. And way back in time, Avra Cohn, who was in fact married to Mike Gordon, verified a quite complicated chip design. Now this was, there was a lot of controversy over this because she verified 2 levels of a very elaborate design and like not all the levels were verified. So there were issues because the manufacturer made some rather grandiose claims that were not justified by what she actually did. But nevertheless, that is a very substantial proof of, I said, 2 levels of a very big design, and this was a real chip that was built. Quite a bit later, but I see already nearly 20 years ago, the ARM6, this was a real ARM processor. I should say that was already obsolete when he did it because ARM didn't want to give him they didn't want to give him any valuable technology, so they gave him the design of an obsolete chip to verify that. But nevertheless, it is a pipeline processor and has a lot of elements that would be regarded as a seriously non-trivial processor. The nice thing about Mike Gordon's technique is it is super simple. So in fact, I'll be able to give you all the basic principles of his approach in this one lecture. Of course, one could go into much more detail in subsequent lectures about exactly how you treat this and that and that and that. The basic idea works as it says there, hierarchically from very big units down to the smallest units. And the big units can be seen of abstractly, so an arithmetic unit might be seen as composed of various things like adders and multipliers that have been put together, so you can regard them as having big chunks in them. These chunks then can be refined further down to simpler devices until finally you get right down to the transistor level. And all this time, for all these layers of abstraction, you're using the exact same modeling technique. The other great innovation of Mike Gordon was to realize that higher order logic was the way to do this. So just to remind you, the key difference between higher order logic and first order logic Well, I guess there are two. Firstly, everything is typed in higher order logic. And secondly, you have functions are built into higher order logic, as well as Boolean valued functions. And it's very natural to imagine a time signal as being a list of Booleans or a function from integers to Booleans, things of that sort. So that was built into the logic and built into the type system. So it's worth stressing his adoption of higher order logic looked totally weird at the time, also to me, because for people who are familiar with logic, higher order logic was just one of those crazy things that existed out there, but no one would, certainly the logicians who had studied it before didn't see any point in it. It was kind of weird and outdated. Okay, the key idea of Mike Gordon's technique is simply that every device is a relation. I mean, that is it. If you want to carry away one slogan from the entire lecture, it's those three words: devices as relations, or if you like, devices are relations. So what you see there is a little box with dev telling you it's a device. It has 4 wires labeled A, B, C, D. Now, you might imagine that the A and B are the inputs and C and D are the outputs. And you might want to model C and D as functions of A and B. That is the natural way to model a device like this. So the real genius for Mike was to realize that that is wrong, that it really works better to say, never mind inputs and outputs. We're going to regard this simply as a relation, and we want to have a logical formula stating the allowed combinations of values for A, B, C, and D. Why is this better? Well, I think it might help if you look a bit lower level and look at that weird-looking thing which is meant to be a transistor. So that thing that says G, S, and D, so that's what in my teen years was called a field effect transistor. I think that is a very archaic terminology now. Anyway, when the gate is high, the source and the drain are connected. Notice there's no inputs and outputs. Well, I guess the gate is an input, but neither the source nor the drain is an input or an output. What happens, rather, is they get connected. So a functional model of that transistor wouldn't make any sense, but a relational model does. And in fact, that formula there, I mean, that's just an implies, right? So that formula says, if G, then S equals D. And that logical formula captures the behavior of the transistor. Now, the cool thing is what it says on the bottom of the slide. The things on those wires don't have to be bits. Depending on your level of abstraction, they could be anything you want. They could be words, they could be integers, they could be, so when I say they're signals, so they could be some kinds of functions. So this very simple idea of modeling devices as relations is quite independent of what is flowing along those wires. And I guess you can imagine already that you can decompose this all the way down and imagine that device as being built from other devices. How we do that is by composition. So you imagine these two devices here, and again, you'll be tempted to think of them as functions, so you might be tempted to think X is a function of A, B is a function of X. But again, we're using relations. The first device is got that formula S1, which we're writing it with its free variables distinguished as A and X. There's S2 over there, it has X and B, and of course the formulas, S1 and S2 are formulas capturing the meaning of those two devices. So when we connect them, so we just make a wire connecting them, all that is happening is now the value of X has to be the same because they're connected by a wire. So the conjunction of the two formulas expresses this device here, which you will note still has a x and b, only now there's one unique x. Now, very often when you connect two devices together, your idea is that x should be hidden. You don't want anybody else attaching anything to x. So the idea of somehow putting this in a box is expressed with an existential quantifier. Now this may need another little bit of explanation here. Clearly the use of a bound variable, now x has become a bound variable, which means x is not visible outside. So syntactically, this is beautiful because we have written a formula now in which a and b are still visible, and you can imagine them being then connected to other things, but x is no longer visible because it's constrained by a bound variable. Now you might say, well, I would rather use for all or something, but you see, exists is simply asserting that there exists a value on that intermediate line. If you put in for all instead, you would be saying that it's true for both true and false, and that's just likely to be false because it doesn't make sense there. The thing that the logical meaning of this is that there exists a possible value for x. If for some reason not, now one could imagine that those devices are such that connecting those two lines together would for some reason not be possible, that it's not actually consistent with the meanings with those two relations. And I think because you can always imagine physically connecting the wires, at least in my mind, I always imagine in the real world something catching fire. Anyway, we will be talking about both implementations and specifications in the same way. But in particular, in hardware, we are always composing devices together to make bigger devices. So we put transistors together to make gates, you put gates together to make flip-flops, you use flip-flops to make shift registers and counters and adders, and so on and up you go until finally you've got entire processes, and you've got all these layers and layers of things that have been composed together. So when you look at a full processor, you don't immediately go right down to the level of transistors, but you look at it in terms of these still relatively abstract components. So an implementation is very naturally going to be the composition of other devices. Specifications can also be composed, and it can be if you look at people who are in the business of doing specification languages in a clean way, they are also very interested sometimes in composing specifications. And so our ability to compose things is also then very useful in the world of specifications. But you might find simply that the specification of what you want is simply some formula or other. And actually it doesn't matter, because whether the specification is composed of smaller specifications or given directly by a formula, at the end, everything's a formula because we're working in logic, and formulas are all we've got here. So everything we're looking at is a formula. So what we are then doing, if you're trying to prove that the implementation of a device, that is to say, a big bunch of gates and so on wired together, if you want to prove that that satisfies a certain mathematical formula, the strongest thing you can do is that if and only if there. So if the implementation is logically equivalent to the specification, so they contain the same variables, and let's say the same input-output relationships hold, that is the strongest thing you can hope to prove. It's not always possible. And the reason it's not always possible is that there are typically a lot of don't care situations. So this one direction, that is to say, implementation implies specification. What that means is, remember, the implementation is a formula which has for all the possible wires coming out of it. Actually, it's kind of useful if you think of a big chip, with all the pins sticking out. And the pins are not actually labeled as inputs and outputs. They're just pins. So you think of all those pins, and you think of all the combinations of ones and zeros that are allowed on those pins when the device is working. And what you would like is for every one of those combinations of ones and zeros to be permitted by the specification. And if you've done that, then you have basically, it's a safety property, I guess you're saying. Everything the implementation can do is permitted by the specification. Now we've got a little problem here. There is a very simple implementation that satisfies all specifications, and it works like this. You take your power, that is 1, you take your ground or your earth, that is 0, and you connect them by a wire. That says 1 equals 0, and it will satisfy every specification. Now, of course, when you turn the power on, either your power supply or your wire will melt. So you've got a problem here. And as I said, every modeling method has its limitations, so you need to be aware of this. Anyway. Well, that happened. Okay, so I want to look now in a little more detail at the stuff Mike Gordon did. Sorry, I'm getting a bit nostalgic here. I can remember this back in like 1985 or so when he was doing this and writing his reports. So you have your P-type transistors, your N-type transistors. There is your ground and your power. So this is really simple. And of course CMOS, which is complementary metal oxide semiconductor. So you see a P-type transistor is given by that formula on the top left. And I'm sorry, I see I've not been very consistent with my arrows. But that is not G implies D equals S. And the next one for the N-type transistor is G implies D equals S. So these transistors are, that's why they're complementary. You see, you have these two kinds of transistors where one, the gate has to go low, and with the other, the gate has to go high. The ground, which is the earth of your power, and is false, and the power supply is true. And we can put this into Isabelle incredibly easily. Now, it's kind of interesting that if the kind of work still being done in this method is still done using versions of the Hall system, because this is how culture works. Hall was used for hardware, and people are still using Hall for hardware, even though Isabelle's own formalism is every bit as strong and can do all this, but cultures develop around tools, and that's just how it goes. But we can do this as shown right there. Now, let's develop an example. So we're going to see a full adder, and we're going to prove it equivalent to its specification, and so forth. So this is a full adder. I hope you've all had a hardware course somewhere and know what a full adder is. So there you have A and B, which we understand as inputs, even though, of course, our relational semantics doesn't know about inputs and outputs. On the right side, we have the carry in. So this is 3 bits being added, and we have a 2-bit sum coming out. So the sum is going to be the bit in the current position, and the carry out will be a bit going to the next position. And that formula at the bottom of the slide is telling us what should be satisfied. So you can see that the carry out is worth double everything else. And there we turn this into Isabelle, and it looks like that. What is that? That is a whole bunch of transistors implementing a full adder. And by the way, and I might end up repeating myself, but whatever, we can see now where some of the difficulties creep in. So I mentioned a while back that if I connect the power to the ground, it will prove everything, but that's kind of obviously stupid. And anyway, it will catch fire. Now you see though, there you've got all those transistors. There's power at the top, there's ground at the bottom, and it's actually not immediately obvious that no short circuit can occur in that. So you might wonder whether there is any risk that with some combination of inputs to this thing, all of those transistors from power to ground on some path or other would all join together and make a short circuit, which would of course cause the chip to melt. And this 0 = 1 situation would also mean that for that combination of inputs, any specification would be satisfied. So it's satisfied, in a sense, it makes sense. The specification isn't violated because the device no longer exists because it's melted. So in a sense, yes, it's a safety property. So it turns out there is no danger of this, and in fact, we actually prove it, though we don't prove it explicitly. Anyway, there is our full adder as transistors, and this is the same thing converted into Isabelle. Now, you should be asking, how do I know that I got this right? How do I know that I didn't make a mistake while typing in all that stuff? Of course, I would say here I copied it all from the Hall version. But what is the real answer? To do this properly, you need hardware design tools that directly output this sort of stuff. So there are in fact tools, I think, I'm not very good at this, but I think called VHDL or something, languages in which you can describe hardware implementations in some kind of hardware description language, which on the one hand, this language goes straight to silicon, and on the other hand, the very same logic goes straight to some kind of verification tool. So there is no human, so if there is an error, it would be the same error on the silicon as on your hardware description here, that is your logical description, so that what you are verifying is indeed the same thing as what has been written to the silicon. Okay, so anyway, that is that huge formula, and you can see now how we have added together a whole bunch of things involving N and P transistors, and then there's a whole bunch of existential quantifiers at the top for all the hidden wires inside. And the actual wires that are visible, if you can just see at the top, A, B, C in, S, and C out, are the visible wires. So that is that relation represents a 1-bit full adder. And there at the bottom of the slide, the theorem there is saying that the add-1 implementation is equal to the add-1 specification. I don't think I gave you the specification as that identifier, but I did give it to you as a formula. It is simply that 2 times the carryout plus the sum equals the sum of the other 3. And we can prove this in one rather clever line. So you see at the bottom there, a call to the simplifier, where we expand out all the definitions and we do something clever. That last thing, so this is a clever trick. That last theorem, which has the arrow coming out of it, is saying, if I have a formula of the form exists B such that P of B, where B has type bool, you can get rid of the quantifier by saying, well, either P of true or P of false. That makes sense because there's only 2 Boolean values. It's a very simple way of getting rid of the existential quantifiers. Now, it's kind of brutal because we have, I guess, 11 variables there, so I guess this could expand into 2 to the 11th copies of that thing. And I guess they simplified down pretty quickly because it didn't actually take very long. Okay, now we want to make an n-bit adder. Now, if you know your hardware, you know this kind of adder is actually crap because it's a ripple carry adder and the delays are terrible, so no one would really use this, but never mind. It's a nice simple circuit, and you can see that it's composed of single-bit full adders joined together. So, I mean, the nice thing about this is we are able to see how you make a bigger device out of smaller devices. And what's also interesting is you got your 3 dots in the middle, which might be worrying, but of course it just means it's a recursive construction. So there is our correctness formula, which is simply that, again, you have the A and the B and the carry in, where I guess A here must be an n-bit word and B is an n-bit word, but carry in is just a single bit. The sum will be an n-bit word, and the carry out, you see what the formula is saying is you take your carry out, which is a single bit, and multiply it by 2 to the n, and that is the relation that should hold. So I understand this is slightly tricky to read because there's no indication of the types in that formula there. But the formal version, the Isabelle version, of course, that will be clear. So there is our cascade of full adders and the recursion. And finally, the specification is just a mathematical formula. So here we have an implementation which is hierarchical. And if you were to add up all the transistors in that, of course, it would be quite a few. But the specification here is not composed in any way. It's just a little formula. Okay, so I talked about this already. S, A, and B are n-bit words. And what we've got now, we have to define, can you see there, there's a thing called bits val, which converts yes, if you have a thing which represents a word, it gives you, in the case of the length of the word being 0, it gives you 0, so a 0-bit word can only have the value 0. And for a longer word, it takes the bit value of f of n and multiplies that by 2 to the n there, and then adds in recursively the values for the rest. And I think I forgot to mention bit val, which must have gone by on a previous slide. So bit val simply maps f to 0 and t to 1. So bit val is the value of a single bit, where bits val is the value of n bits, those bits generated by this function f. So, by the way, you might say maybe f should be a list or something instead. Well, I mean, you could do that, but we didn't. And now you have the specification of the adder there as taking those 5 arguments, a, b, etc. And there you see the formal version of the formula at the top of the slide, 2 to the n times the bit value of the carry out, and so on and so forth. And see, those invisible blue lines are showing connecting the variables in the top of the formula there. I see we go from S, we call it sum down there, to variables in formal version at the bottom of the slide. Okay, now for our implementation, as mentioned before, it's recursive like this. So we're going to just write a recursive function. And we can see here, for example, In the case of 0, what is a 0-bit adder anyway? Well, you have to imagine that dotted, there are no bits whatever, and it just connects the carry in to the carry out. Whereas in the recursive case, somehow this internal wire that connects the first adder to the rest is there. You see where it says exist C, which is a carry. So this n plus 1 bit adder, in this recursive case here, you see it says that holds if there exists a carry, so that we can have an adder for the first n bits. So that is the general n-bit adder for the first n bits there, returning C. And then we use a 1-bit adder to take the very last things, that is an and bn, combine that with C, and we get sum n and carry out. And again, the relational interpretation is important here, because it kind of weirdly, especially because a, b, and sum are all functions from natural numbers to the corresponding bit. So it would be very hard to make this work as inputs being turned into outputs. And yeah, look, the longer you look at that, the weirder it looks, actually. Okay, now we're going to try and prove this thing correct. Now, I call this partial correctness because we're only proving one direction here. As I mentioned before, the simplest correction, or the minimal correctness proof, is to show that everything the implementation can do is allowed by the specification. So we set up an induction. By the way, where you see arbitrary C out, I hope it's clear that when you got the idea of a carry thing that is going through in recursive calls, you need to allow it to vary, because there's no reason why the carry in the inner call should be the same as the carry for the thing as a whole. So making it arbitrary allows it to vary. When we do our induction, I guess the base case is going to be trivial, because it's just 0. And the interesting thing will be the induction step. So as you can see, the cursor at the moment is right after the case suck n. So what we're able to look at is the assumptions going in. So we have the adder imp, which I guess is carried through, as well as, the adder imp thing is carried through from the one in the theorem statement itself. The one above, the one that says adder imp implies adder spec, is of course the induction hypothesis. So the induction hypothesis says the adder works for size n, and of course we're trying to show that the adder works for size n plus 1. As you see at the bottom of the slide there. So we've got to use our induction hypotheses, and what are we doing? So there is the internal wire that we're getting. So how do we have this? Yes. So we know that we have an implementation which is n plus 1 long, and we also know that the implementation, that if the implementation is correct for n, then the specification is also satisfied. And I guess it's also true that if we have an implementation for suck n, it includes inside it an implementation for n, right? That's the dashed box, is the implementation for n. So that implementation is present, and by the induction hypothesis, it is correct. So when you look at the statement of the formula, what we are obtaining, we're actually assuming now that we have the specification satisfied for the n-bit addition of a, b, and n. So that's just above where that third arrow is. So we are able to assume that the adder specification holds for n. We now have the full bit adder, the 1-bit adder for the last one, and we somehow need to get the conclusion from all of this. So we do a calculation here which is very, very ugly, which is actually, it is just very elementary arithmetic here. So yeah, as it says, we're doing some very elementary rearranging. What have I done there? Replacing outputs by inputs. Yes, what I think that is doing is using the correctness of the 1-bit adder to say that given that we have a 1-bit adder here, that we know that the relationship that will hold between those various bits. And it turns out this is actually quite an easy thing to prove, and that is great. So as I said before, we have proved that the implementation implies a specification. So great. Oh dear, another unfortunate situation here. Okay. Why do we want to prove equivalence? So I proved implementation implies specification. Now, if I prove the opposite direction, specification implies implementation, why is that good? Well, that is good because it is always possible to add two n-bit integers. That is to say, all combinations, all of the, 2 to the 2n combinations of inputs are plus an extra factor of 2 for the carry in. Every one of those, the sum can be expressed using arithmetic and will satisfy the specification. So what we want to do is show that for every possible combination of inputs, the specification can be satisfied. And that means if we can prove the two to be equivalent, we've proved the implementation is also satisfied. That is important because remember I said if you get a short circuit, that is a 1 = 0 in these implementation under certain circumstances, that represents a thing that can't exist in the real world. So we can show that that never happens by showing that every combination of, in particular, of what we regard as input values has an allowable assignment of values to the other values of the device. That way showing that there cannot be a short circuit, because of course a short circuit would logically amount to the formula false. Okay, so now we're on our way to try and prove the opposite direction of the implication. And I guess one natural way to do this is you see this formula here. This looks quite a lot like the formula describing the implementation, only it says spec everywhere. So this is not talking, it's not talking about implementations at all. It is talking purely about specification. It is talking purely about mathematics. But if you can just look at that, you can see that that looks an awful lot like the property that the implementation is satisfying, and so it will be a useful lemma to prove. So we want to prove this formula, and we use our tricks, and the trouble is we have a mess. Now, you don't need to look at that mess in detail, but the thing is, I got 16 sub-goals here. That's more sub-goals than anybody wants to look at. And here, again, as I say, when something like this happens, you have to look carefully and see if you can see anything funny happening. Now, in particular, you might say, well, I'll try sledgehammer now, but I don't think sledgehammer is going to do any good. Nevertheless, if you look very carefully, you might see something. So let's look at sub-goal number 1, and the formula at the end, it says bits val Sn equals something. Well, what is bits val Sn? It is the value of an n-bit word. What's it equal to? It's equal to the successor of 2 to the n plus other stuff. Now, what is the maximum value of an n-bit word? It's 2 to the n minus 1. So there's no way that 2 to the n minus 1 can be equal to something which is bigger than 2 to the n. So that equality there is false, and in fact, if you look at the others, they all have the same property. So we need some way of catching this. So what do? Firstly, I prove what I just claimed, that the value of an n-bit word is less than 2 to the n. And then there's a very funny trick you haven't seen before. So can you see, looking at the lower red arrow, I have the theorem just proved about bits value and 2 to the n, but I have plugged in specific values a, b, and s. Why do I do that? Okay, naively I do that because then the simplifier works. Why does the simplifier work when I plug in those 3 instances with specific variables when the original theorem with its quantified variables is actually stronger? And I guess the answer is the simplifier isn't dumb enough to notice that these quantified variables could, if replaced by A or B or S, solve stuff for us. So we are helping the simplifier by giving it the exact instances required of the lemma just proved. And it turns out, in fact, linear arithmetic is going to do this. So it knows that that thing, let's say bits val an, is less than 2 to the n. With that knowledge, and then when it sees that identity between that exact number, bits val an, and something else, it will see the contradiction, and then it will be proved. So it will work, and it will be very easy. So now when we want to prove that the adder specification implies the adder implementation, it's going to be completely trivial because the thing I just proved is exactly what we needed. And now we have complete equivalence between the specification and implementation. Okay, and that finishes the verification of the ripple carry adder. So what did I just do? Okay, this thing called of that we just saw. In general, if you have a theorem, so THM there, it refers to any theorem you might have floating around. If you want to plug in specific terms, you can just write the terms that you want, like they're A, B, C. If actually you can't think of anything good to put for B, say, you could use an underscore as a placeholder, and then that second variable would be left alone, and you could still plug in something for the third. You can also plug in terms for variables by name. So whereas the first one is simply the left to right position of a variable in the theorem, this second one is I am naming a particular variable that I want to replace by a particular term. Now the big of is quite a different thing. Here, we're not plugging in variables. We are plugging in entire assumptions. So remember a typical theorem. Every theorem has some n premises or assumptions, above the horizontal line that the conclusion depends on. With big of, you are saying, okay, use this theorem here to prove, let's say, the first premise of my theorem over there. So you are able to then generate different instances of theorems, not by plugging in terms, but by combining it with other theorems that prove things that you want. This last one, well, we've seen the simplifier, of course, from the very beginning of the course. Now, normally, a theorem that you have will not need to be simplified because you would prove it in its simpler form, because anything else would be kind of dumb. But if you have just made an instance of a theorem by, let's say I replace x by 0, then probably this theorem statement, which now has a bunch of zeros in it, can be simplified, and I can make a simpler instance of the original theorem. So that is useful to do. And what I'm saying here in the last line is that you can do a whole series of these things one after another. So I can take a theorem, I can say of a couple of things, comma, I can use big of to prove something using some theorem, and comma, simplify to simplify the result. So that kind of stuff, this is one way in which you can use, take existing theorems and generate instances of them quite easily. And that's it for now.